Hello and welcome to Calculus Lesson 7.3, Applications of the Dot Product. Now we actually saw an application of this in the previous video, so I'm going to start off with that one. So one application of the dot product is something called work. This is a concept that we go over in physics, but nonetheless, let's look at an example of this again. So let's say I have some kind of a ramp, and on that ramp I have a wheelchair. Now there is a force being acted upon the wheelchair, and the force is going in this direction. Now force is a vector, it has magnitude, it has direction, so I symbolize it with, an appropriate letter with the arrow on top. Now this wheelchair is getting displaced up the ramp, so this is the direction of its delta D. Again, it's displacement, it's a vector, I put an arrow on top, and the angle between these two vectors is 30 degrees. So usually the way a question like this would be worded is that the force applied to the wheelchair is 30 degrees above the ramp. Okay, it wouldn't tell you that it's 30 degrees from the displacement. You have to put those other pieces together. Okay, so I know a couple things here. I know the displacement is 300 meters. Rather, this is the magnitude of the displacement. I know the magnitude of the force is 500 newtons. Okay, so the question wants me to find the work done. Okay, so if you recall, by definition, work is the dot product of force and displacement. So that's our starting formula. Dot product of two vectors means I take the magnitude of each vector, I multiply them to each other, and then I multiply by the cosine of the angle between them when they are placed tail to tail. All right, so here we go. Force is 500. The displacement is 300. Cosine of the angle, we have cosine of 30 degrees. Make sure your calculator's in degrees. And you end up with work is equal to 129,904 joules. And we saw that last time as well. The unit for work is joules. And another interesting conclusion I want to remind you of. The result of the dot product is a scalar quantity. Okay, this is not a vector. If it was, there would be a direction. Okay, we don't have any direction here. This is just a number. Now, the other thing I want to remind you is whenever you're calculating work, in physics, those of you taking physics, you already know this because I've constantly reminded you of this. For those of you who never took physics, you have to make sure that when you plug in values, force is in newtons and displacement is in meters. So, for example, if a question tells you that, let's say, a car is displaced 0.6 kilometers, you have to convert that to meters. So that would be 600 meters. All right, so there's that. Let's do another example. So this one's not so much application-based, just some knowledge and understanding. Example 2, find the angle between each pair of vectors. Okay, so let's find the angle between vector A. Vector A is 1, 5, and vector B is 8, -3. All right, so whenever you need to find the angle between two vectors and you're given the vectors, a really nice quick way to do it is by using the dot product, right? I've got the magnitudes and I've got the cosine of the angle between them. Okay, so here we go. So I know that I have two vectors here, A and B. So the dot product A dot B is equal to the magnitude of A times the magnitude of B times cosine of theta. Since I'm looking for the angle, that means I have to rearrange for cosine of theta, which will eventually let me isolate for theta. So cosine of theta is equal to A dot B divided by magnitude of A times magnitude of B. So what I'm going to do is actually just plug in the vectors as you see here in this formula in the same format. Okay, so here we go. So A dot B, so A is 1, 5, so that's 1, 5 dot 8, -3 divided by the magnitudes of the two vectors multiplied. Okay, so I'm just going to stick the vectors into these absolute value brackets, okay, because I'm looking for the magnitude. So magnitude of 1, 5 and the magnitude of 8 comma minus 3. Okay. Now you have to understand how to break this, I guess, expression down. If you have the dot product of two vectors, that means that you take the product of the x values and you add to that the product of the y values. So that means that the numerator is going to become 1 times 8 plus 5 times negative 3. Okay. Multiply the x's, add to that the product of the y's. Now magnitude of a vector, okay, what you have to think about is, okay, let's say 1, 5. That means this is a vector. If you were to start the vector from the origin at 0, 0, then this vector, you would go 1 space to the right, 5 spaces up, and the arrow connecting the origin to that new point is your vector. Okay, so if you want to know the magnitude of the vector, essentially I'm looking for the length. Okay, so let's just do this one. I'll show you really quick. So if I have x and y, so this vector 1, 5, so 1 unit here, 5 units up here. So the vector looks like this. This is 1, 5. If I want to find the magnitude of that vector, I have to use Pythagorean theorem. So I've got some component along the x direction, and I've got some component along the y direction. I know that if I have this right angle triangle, I know the base of that right angle triangle is 1, the height of that right angle triangle is 5, and the hypotenuse is the length of the vector 1, 5. Right, so I use Pythagorean theorem, and that's what I'm going to do here. Okay, so the magnitude of 1, 5 is the square root of 1 squared plus 5 squared. And then this gets multiplied to the magnitude of 8 comma negative 3. So multiply that by the square root of 8 squared plus negative 3 squared. So just be careful when you're crunching these numbers. All right, so what do we get? Numerator, we're going to have 8 minus 15. And in the denominator, let's do these separate. 5 squared is 25. 1 squared is 1. 25 and 1 make 26. That's root 26. 3 or even negative 3 squared, that's 9. 8 squared is 64. 64 and 9 make 73. So that's root 73. Now, really you just have to figure out what this is equal to. But remember, this entire piece on the right is equal to cosine of theta. So that means theta is going to be equal to the inverse cosine of this argument. So I'm just going to simplify it really fast. 8 minus 15, that's negative 7. And in the denominator, I still have root 26, root 73. I mean, this is something you can just grab your calculator and punch in, right? So grabbing the calculator, make sure you're in degrees. So inverse cosine of negative 7 over, and I'm being very careful with my brackets here, root 26 times root 73, close bracket, and end up with 99.246 degrees. Okay, if you want to simply give this to 3 sig figs, that's fine. You can call that 99.2 degrees. Okay, so that's the angle between the two vectors. All right, so let's move on to the next topic. Okay, so now that we know how to do dot product, there's a really important application of dot product. And that application is called vector projections. And this is going to be the rest of this section 7.3. Now, what I want you to imagine is this. I have two vectors, u and v. And these vectors I'm going to place tail to tail. So let's say I have these vectors, u and v. Like I said, they're placed tail to tail. Imagine I have some source of light. So let's say I have light coming in from this direction. Maybe it's sunlight, maybe I'm holding a flashlight, but there is light coming in. Let's just say it's a flashlight. What I know is that vector v is going to cast a shadow onto vector u. And that shadow is going to look something like this. Okay, so take note of the length of that shadow. All right, so its x length or its horizontal length is the same as the x or horizontal length of v. hopefully that makes sense. If the light is coming down at a 90-degree angle, okay, so that means the shadow cannot exceed the length here. So hopefully that makes sense. So what we'll say is that this red arrow, this is the vector component of v in the direction of u. Right, you can clearly see that red arrow is in the direction of u, and that is only one piece of it. Right? You know how to make components. If I have vector v here, I can break it up into an x component, vx, and I can break it up into a y component, vy, where vx and vy are perpendicular to each other. Okay, so I can say that vx is along the x direction, but here I already know that vx, or whatever I'm going to call this, which I'll show you, it's along the u direction. Okay, so this thing overall, this red arrow, this is called the projection of v onto u. That's really all it is. Okay, so the way I want you to think of the projection is, and this is how you're going to write it, so the projection of v onto u, we write as proj vector v and then a small little vector u. Okay? So the projection of v onto u is the shadow that v casts onto u. Now there are many, many applications of vector projections. We're just going to barely touch the surface here, but if you continue studying this further, you will see more and more applications of vector projection. All right, so let's look at some scenarios or some cases. Okay, we'll look at 3 cases in particular. So go ahead and label number 1, number 2, and number 3 on your sheets. All right, so the first case, we're going to look at something like what we already had. We're going to have vector v up on some angle and vector u, well, there's an acute angle between u and v. So there's theta. Okay, case number 2, we're going to have u still going towards the right. This time we're going to have vector v up at some angle, and this angle is no longer acute. Okay, in the third instance, we're going to have still vector u going to the right, and this time v is going to be at a 90-degree angle. So we're going to look at all 3 of these cases. Okay, so remember the idea here, think of it as there is a source of light coming from this direction. Okay, in all of these cases, there's just a source of light coming in, and v is going to cast a shadow onto u. Okay, so in the first case, this is the case where theta is between 0 and 90 degrees. And what I see, if I want to draw the projection, what I do is take my vector v and draw a vertical dashed line. Well, not necessarily vertical, let me just change that. You draw a dashed line from v to u such that that dashed line touches u at an angle of 90 degrees. In this case, it's vertical, but as we'll see in some later examples, it's not always vertical. You have to just make sure that that dashed line meets the vector u at 90 degrees. Okay, so if I do that, then I can see the projection is going to look something like this. Okay, so there's that projection right there. And what I see is that the projection of vector v onto vector u is in the same direction as u. Now, if you're wondering if that is an obvious consequence, it is, but it's not always going to be the case. Okay, so for example, consider case number 2. This time my angle is between 90 and 180 degrees. This is an obtuse angle. Now, if the light is coming from the top, the shadow of v is not going to be cast onto vector u, it's going to be cast on this side this time. And so what I'm going to do is, well, just draw a dashed horizontal line here. So this is the line that u exists, and v is going to cast a shadow like so. Okay, so there's the shadow. From V, I draw a vertical dashed line down to where U is, or where the line of U is. So there's the 90 degrees. But this arrow down here, that's the projection. Okay, so what I see here is that the projection of V onto U is in the minus U direction. All that means is it's in the direction in the opposite of U. Okay. And last but not least, here we have theta is equal to 90 degrees. Now, you know, if it's noon and the sun is at its highest point, you're not going to cast a shadow. Similarly, if your light's coming from the top, V is not going to cast a shadow onto you. And if V doesn't cast a shadow onto you, that means there's no projection, because the projection is, after all, the shadow. There's no shadow here. So therefore, the projection of V onto U is equal to 0. Now I want you to think about that for a moment. The last time we saw that when two things are perpendicular, that certain quantity is equal to 0 was dot product. When you have dot product, you deal with cosine of the angle between the two vectors, and cosine of 90 is 0. So this is already giving us an idea that the projection of a vector has something to do with dot product. Okay, now what I've been showing you so far, I keep drawing the projections as these red arrows. And these red arrows, while they're projections, they're vectors at the end of the day. And you know that vectors have magnitude and they have direction. So what we're going to do next is spend some time figuring out, well, what is an expression for the magnitude of the projection vector, and how can we determine a generalized way of stating its direction. Okay, so let me just finish off here by stating that the projection, while it is a shadow, this is a vector. And so sometimes what we'll do is write it like this. So projection of V onto U, while this is a vector, if I was to put these two absolute value symbols around it, this would imply the magnitude. So if I have the magnitude of the projection vector and then I stick a direction next to it, now this entire thing becomes a vector. Now what we're going to have to focus on is how do we figure out the magnitude of the projection and how do we state its direction. It won't be so bad. Okay, so before we move on to the next page, I want you to just focus on this case number 1 here. In case number 1, I had vector u, I had vector v, the angle between them was theta, and essentially what I have here drawn out is a right angle triangle. The base of that triangle is the projection of v onto u. The hypotenuse of that right angle triangle is v. And this side, well, we're not going to concern ourselves with what we call that, but we have the projection of v onto u on the bottom, theta, and then the hypotenuse is v. So that's what I'm going to start off with on my next page. Okay, so I have, this is going to be vector v, and the bottom here, this is the projection of v onto u, and then I've got this other vector here, which I'm not really going to concern myself about. This is 90, this angle here is theta. What I want to do is come up with an expression for the magnitude. Now you know that the magnitude of a vector is the length of that arrow right there. And since this is a right angle triangle, I can figure out that length really easily. Imagine for a second we have this scenario. Imagine you have a right angle triangle. You know that the hypotenuse of the right angle triangle is 5. You know that this angle is theta, and you're looking for x. The two sides of interest here relative to angle theta are the adjacent and the hypotenuse sides. Adjacent and hypotenuse tell us that we're using cosine. Cosine of theta is equal to adjacent over hypotenuse. And so if we rearrange for x, it's 5 cosine theta. So when you're looking for either the x or the y components of a right angle triangle, it's always equal to the hypotenuse times sine or cosine of the angle. Cosine if it's for x and sine if it's for y. And so similarly here, I'm looking for the x. That's the projection. So the projection of v onto u is going to be the hypotenuse, right? But not just the hypotenuse. I'm looking at the magnitude of the hypotenuse times cosine of the angle, theta. And all of this is, what it's telling me is the magnitude of the projection. So the length of the bottom side is equal to the length of the hypotenuse times cosine of the angle between them. And that's really all it is. So what I have so far, this right here, this is the magnitude of the projection. Now remember, for a vector, you need magnitude and you need direction. So in some cases, you might look at this and say, well, it's in the direction u, and that's fine, but it would be nice if I could be more specific. Right? So what I'm going to do here is try to figure out what a unit vector is in the direction of u. Because if I can figure out a unit vector in the direction of u, well, this will be much better. This way I don't have to change the magnitude of my vector, but at the same time I can quote which direction it's going in. I'm going to make a very important point here. If you want to make any vector a unit vector, you simply, and I'm going to finish that sentence in just in a moment. Okay, so remember what it means to have a unit vector. Okay, a unit vector is a vector with magnitude 1. Okay, that the length of it is just 1. If I take any vector, okay, so actually let's just go back to that first page here for a moment. If I go to any vector, let's say the vector 1, 5, which was A, I found that the magnitude of that was, well, that's here. And this is how I determined what the magnitude was, Pythagorean Theorem. It was root 26. Square root of 26 is not 1. But if I wanted to make, well, the magnitude become 1, all I have to do is divide by root 26. Okay? If the magnitude of a vector is 5 and you want to make it into 1, how do you make 5 into 1? You divide it by itself, by 5. You divide it by its magnitude. And that's what we're going to say here. If you want to make any vector a unit vector, you simply take the vector and divide by its magnitude. That's it. Okay, so that means this new vector will have magnitude 1, but it will be going in the same direction as whatever it was originally going in. Right, so if I have vector u, let's say, if vector u is 5 units long and I divide it by 5, now I have another vector here. Usually I call the unit vector u hat, but even so, in the book they don't use the hat symbol. They just use the regular vector symbol. But the idea is it has the same direction as u, but it only has length 1. Okay, so what I'm going to do then, so based on this definition, take the vector and divide it by its magnitude. So I take vector u and I divide by its magnitude, right? So this should be u hat. This is the expression for a unit vector. U hat is equal to u over magnitude of u. All right, so now going back here, I already have the magnitude of the projection. I have to give a direction. And I know the direction is in the direction of vector u. Okay? So what I can say is that this is in the direction of u hat. Okay? So the projection of v onto u is equal to v cos theta. There's the magnitude. And I say it's in the direction u hat. Now, like I just said a couple moments ago, the book doesn't use the hat symbol. So even though I'm showing you this now, I'm showing you so that when you study mathematics next year in university, if you ever see the hat symbol representing a unit vector, you'll remember this and say, okay, well, that's the true symbol of what it is. Here, we're not going to be using the hat symbol. We're going to always use the right side here, u over magnitude of u. So in reality, what we're going to write is this. V, magnitude of v rather, times cosine of theta, times u over magnitude of u. Okay, so this is the formula for the projection of vector v onto u. Okay, so very important, excuse me, that you remember that. Now this is assuming that the projection is in the same direction as u, right? Because that's what I'm trying to imply here. It's in the same direction. But based on our second case here, so let's go back to the cases, it doesn't necessarily have to be in the same direction as u. It might be in the opposite direction. Okay, so if theta, for example, is 135 degrees, that's not between 0 and 90. And that means that my projection is in the opposite direction of u, in the minus u direction. And so if that's the case, all we have to do is multiply by minus u over u. So if the projection is in the minus u direction, then the unit vector will also be in the minus u direction. Okay, so then that unit vector would look something like this. Minus u over magnitude of u. That's it. Okay, magnitude of u, magnitude of minus u, they're the same. Okay, so we have an expression for the projection. Now, I want to show you another method of determining the projection of one vector onto another, and that's going to come down to this cosine of theta. Okay, remember earlier I said that the fact that the projection of one vector on another is 0, so the shadow that one vector casts on another vector is 0 when the two vectors are perpendicular to each other, and this is very closely related to dot product. Okay? Well, cosine of theta shows up in dot product of two vectors as well. So what I'm going to do is replace the cosine of theta with an expression for dot products. Maybe the question doesn't give you the angle between the vectors. Maybe it just gives you the vectors, like in the second example that we saw. In that case, you're not going to want to have the formula that looks like this. Okay, so let's take a look. All right, so we're going to go back to the expression for the magnitude here. So from here, we're coming down. Okay, so the expression for the magnitude is the magnitude of projection of v onto u is equal to magnitude of v times cosine of theta. But like I said, earlier, we saw that cosine of theta is equal to u dot v over magnitude of u times magnitude of v, right? That's just dot product rearranged, and that's a dot in there. Okay, so what I'm going to do is substitute that in. So I have magnitude of v times u dot v divided by, excuse me, magnitude of u, magnitude of v. Okay, what I see is I have a magnitude of v in both the numerator and denominator slots. So those cancel. Okay, so then I'm left with just u dot v over magnitude of u. Okay, so that is another expression for the magnitude of the projection of vector v onto u. Now, like I said earlier, projection's a vector. Sometimes you're going to want to know the direction. So to give it a direction, you simply have to multiply by a unit vector in the direction of u, which is this, right? So I'm going to multiply this by vector u over magnitude of u, okay? So that gives it a direction, which means the overall projection vector, so the projection of v onto u, is equal to, now I want you to pay really close attention here. I've got u dot v in the numerator, so u dot v. Okay. In the denominator, I'm going to leave this for last. In the denominator, I have u, magnitude of u, times magnitude of u. Magnitude of u times magnitude of u is magnitude of u squared. And if you recall, that's the same thing as dotting a vector by itself. We saw this in one of the earlier videos. Okay, so I'm going to replace the denominator with u dot u. And this whole thing is going to get multiplied to vector u. Okay, remember, here I have u dot v divided by magnitude of u. The dot product is a scalar, so that's a number. You take a number and divide it by a number, that's a number. You don't dot a number with a vector. You multiply, right? A number times a vector is multiplication. Dot product is for two vectors. So a number times a vector, okay, that means that this is multiplication. So even though we're using the same symbol of a dot, we only say dot, and it only means dot product rather when there are two vectors involved. If it's multiplication, you have to understand that that's multiplication. Okay, so this piece right here is a dot product over a dot product. This is the scalar. It's a constant k, which we could figure out. K is an element of the real numbers, a constant times u. But this is another formula for the projection of vector v onto vector u. This will come up again in one of the examples that we do. Okay, so we are officially halfway through the lesson. Let's do some specific examples, some concrete examples. Okay. So I believe we're at, let's see here, example 4. Give me 1 second. Well, okay, not formally example 4, but okay, let's call this example 3. Determine the projection of u on v. All right, so let me draw the vectors that would be normally given in the question. So we have vector u like so. We have vector v like so. Okay, so here's vector u and it has magnitude 5. Vector v has magnitude 1 and the angle between them is 50 degrees. So this is all the information given in the problem. Okay, so determine the projection of u onto v. Now, what you're used to is that whatever vector is getting projected on the second vector, that second vector is usually very long. It's not in this case, it's shorter, and that's okay. But the idea is the shadow is getting cast onto the direction that v is facing. So the direction that v is facing, I'm just going to extend v, not the vector, but I'm going to extend the line that it's moving towards like this. Okay. Now, remember I said you draw the projection of one vector onto another such that it makes a 90-degree angle with the other vector, or in this case, the direction that the vector is going. Okay, so that's a 90-degree angle to the direction v is going, which means my vector projection looks like this. Okay, so that's the red arrow right there. Okay, so this is the projection of u onto v. Hopefully that makes sense. Okay, so since we're trying to figure it out, we need the magnitude of this and we need the direction. Now this problem is not giving us very much information. We don't know what the vector v is, we just know its magnitude. Okay, so we know that the direction of this vector is in the direction v. Okay, so then a unit vector in the direction of v is, well, v divided by its magnitude, right? Because this way it's in the direction of v, but it only has magnitude 1. Since, like I said, we don't actually have v, so for example, if v was told to us in the question, okay, v is 1, 2, it's not, but for example, let's say it was, then you could figure out the numerator here, which is just this. You could figure out the denominator. The magnitude of v here would be 5, square root of 5. And so you would have 1, 2 over square root of 5, and that would be your direction. But that's not what we have here. It's actually a little simpler. Since we don't have any of that information, we just have to state that the projection is in the direction of v. Okay, so we know here that theta is between 0 and 90 degrees. So I'm going to use one of my formulas here. So the projection of vector u onto vector v is equal to, so it's the hypotenuse of the right angled triangle, magnitude, times cosine of the angle between them. Okay, so u is 5. So it's 5 and the angle is 50 degrees. So 5 cosine of 50 degrees, grab your calculator. 5 times cosine 50, we have 3.2 approximately. Okay, so 3.2. And like I said, since we don't have an actual vector to give the direction, we're just going to say in the v direction, or in the direction of v. Okay, so that is the answer here. Of course, if we have the vector, writing this would not be sufficient. You would actually have to state the direction. And well, we'll see that here in the next example. Okay, so that is part A. Part B, determine the projection of P on Q. All right, so let me sketch out the picture that would normally be given. So there's P, and magnitude of vector P is 20. There's vector Q, and magnitude of Q is 30. And the angle between them, you can clearly see it's obtuse here. That's 120 degrees. So when we want to draw our projection, remember this would be case 2. What I'm going to do is draw vector Q, but I'm going to extend the direction where it's facing. I don't have to extend it on the right, but just so we're consistent with the previous problem, I'll do that. So on the right and on the left. So if there's light coming from on top here, the shadow that P casts onto Q is going to look like this. Okay, so that is the projection of P onto Q. Notice that it's going in the negative Q direction. That's important to notice, and so that'll come up again when we actually do our calculations. Okay, so we've got that. Now let's figure out what the projection is. So the projection magnitude of P onto Q is equal to magnitude of P times cosine of theta. Now, you'll probably notice that I left a bit of a space here, and the reason for that is because I'm going to stick in a minus sign. Okay. If you don't stick in a minus sign, what you're going to see is, well, let me show you. Let's say you didn't stick in the minus sign. The magnitude of P is 20. The cosine of the angle, it's cosine of 120 degrees. Now, cosine of 120 degrees, that's a negative value, right? So if you keep this as positive in front, you'll have a negative times a positive, which is negative. But the projection is a magnitude. It's supposed to have an absolute value. It shouldn't have a negative sign. So what I do is I just stick the minus sign in front to counteract the minus from this. So that's minus, that's plus. So 2 minuses and 1 plus make plus. And that's what you want. Okay, so 20 times cosine of 120. So we have minus 10. With the extra minus there, it becomes positive 10. Okay. So it should just be common sense that the magnitude should be positive. Now for the direction, we would say that it's in the direction opposite of Q. Okay, or you could say it's in the negative Q direction, up to you. Okay, so in the opposite direction of Q. So there's the answer to this piece. All right. Now let's do part C. Determine the projection of D, which is 2, negative 3, on C, which is 1, 4. So this problem is a little different than the other ones that we've seen. So far we've been given the magnitudes and we've been given the angle, and we've consistently used the same kind of formula, right? So here's the projection is equal to the hypotenuse of that triangle magnitude times cosine of the angle. And we did the same thing up here as well in the earlier example. And this time we're given the vectors as is. So I want to go back to one of the previous, I guess not slides, but one of the previous pages here. So far we've really been using this formula. This one specifically because we've just been finding the magnitude. If we needed to, we could have gotten the direction from here, but really this is what we've been using. Since in this problem we're given the vectors themselves, we're not given cosine of the angle between the vectors, what I'm going to do is use a different projection formula. Right, so that's where these ones come into hand. So I'm going to be using the one on the right here. So this way I have the magnitude and I've got the direction. So just pay attention to the formula here. Okay, so I'm going to actually take this and copy it down onto the next page. So let's do this. Okay, so take this formula and just write it down here so you have it. So projection of V onto U is equal to, bracket, U dot V over U dot U times U. Okay, so the reason why I wanted you to do that is so that you notice, well, whatever vector you have here as the main vector, this only appears once in the formula. So v only appears here. U, the vector that it's getting projected onto, appears 1, 2, 3, 4 times. Okay, so this way you know where you have to place everything. What we're looking for is the projection of D on C. So what we need here is the projection of D on C. So following the same, I guess, naming criteria, we're going to have C dot D over C dot C times C. Okay, so make sure that's okay. So at this point, we're just going to plug in what we have. So, all right. So I have vector C dotted with vector D over vector C dotted with vector C. All right, so let's fill those in. So C is 1, 4. So 1, 4 is here, 1, 4 is here, 1, 4 is here. And then I have 2, -3 that gets stuck here. Okay. Now I'm multiplying all of that by C. Remember, I keep saying multiply, and that's because I'm actually multiplying this with this. This is going to turn out to be a scalar. It's going to turn out to be a number. You don't dot a number with a vector, you multiply numbers to vectors. Essentially what you have is a scalar multiple. Okay, so here dot product, multiply the x values. So that's 1 times 2 plus multiply the y values, 4 times -3. In the denominator, I'm going to have 1 times 1 plus 4 times 4. And all of this times 1, 4. All right. So what do we have in the numerator? We have 2 minus 12. 2 minus 12 is -10. And in the denominator, I have 1 plus 16. That's 17. So notice we just ended up with a number. And we have 1 for getting multiplied. So what we have here, and again, I want you to notice this, is we essentially have k times u, where k is a constant, right? We have a scalar multiple. So really what we can do, the rule for scalar multiples says that if I have k times ux comma uy, this is equal to kux comma kuy. This is the distributive property, which we saw earlier. So I'm going to take that constant and multiply it to each piece inside. So that means I am left with the following vector, -10 over 17, comma, -40 over 17. So this is the projection of vector D onto C. This is the vector in this direction. So if you find -10 over 17 in the x, -40 over 17 in the y, and you plot those points, you get the overall vector, which is the projection. Okay, we have one more problem we're going to do. And this is, again, a bit of an application question. This is a word problem. Okay, so let's do that. So this will be example 4. Okay, so a store sells 350 pairs of e-shoes. Okay, so maybe there's some fancy name for this kind of shoe. Whatever it is that starts with the letter E. That's really what you need to know. The store sells 350 pairs of e-shoes and 275 of C-shoes in 1 year. Okay, so the e-shoes cost $175 each, and C costs $250 each. Okay, expensive shoes. Part A. Write a Cartesian vector. So remember Cartesian means you have, well, pretty much this. You have square brackets, x comma y. So write a Cartesian vector S to represent the number of pairs of shoes sold. Part B, It's going to be exactly like part A, except instead of writing a vector S for the number of pairs of shoes sold, we're going to figure out a vector P to represent the price of the pairs of shoes sold. So instead of writing all of that again, I'm going to just put these quotation symbols. So that just means see the line above. So write a Cartesian vector, this time P, to represent the price. So not number of pairs, but price of shoes sold. Okay. And then for part C, we are going to find the dot product S dot P and then determine what it represents. Okay, last example, let's do this. All right, write a Cartesian vector to represent the number of pairs of shoes sold. So if we are doing our vector xy, where x is, let's say, E and y is C, you could do it the other way around too. It doesn't really matter as long as you're consistent. So I have 350 pairs of shoes for E, and I have 275 pairs of shoes for C. Okay, so E value, that's x, C value is y. That's how you want to think of it. For part B, write a Cartesian vector P to represent the number of pairs, the price of the pairs of shoes sold. So again, in the X slot, I have to write the value corresponding to E. And for E, it's $175 per shoe. So I stick 175 in here, and the Y slot, that is for C. And the C shoes cost $250 each. Okay, now what's most interesting here is going to be the result of part C, the dot product. So if I have S dot P, that's essentially 350, 275, dotted with 175, 250. And so I multiply the X values together and the Y values. So that's 350 times 175 plus 275 times 250. Now, before I actually calculate this out, I want to show you what the units are here. 350, this is number of shoes. And the 175, that's dollars per shoe. Right, so same thing here, 275, that's the number of shoes. And the 250, this is dollars per shoe, right? $250 per shoe, or pair of shoes. What I want you to notice is that the units shoes cancel, and you're left with dollars. This is how we're going to interpret what the final result represents. So grabbing your calculator, let's see what this is equal to. So 350 times 175 plus 275 times 250. So we have 130,000. And the fact that you've already analyzed the units, you know that this is in dollars. And so what this represents is the amount of revenue of shoe sales. Okay, well, that is the end of lesson 7.3, applications of the dot product. Okay, so stay tuned next time for video 7.4.